Uh, code not work. Is the code working? Okay. No, no, not working. Okay. Let me check the code first. Okay. Try the new one. Try the new one. Is it working now? Okay. Working? The new one? Works? It say it works. Try again. Try again. Okay. Online students, have you checked the QR code, the new one? I just put. Is it working? Still not working? So who is uh, not working? Uh, who is it's working? Working? Why there's someone the work code is working and some is not? Okay. Who's still not working? The code still not working? Oh, or a lot. Okay. Anyway, we can try later at the end of our course again. Okay. If you so let's just start the course first, and then I will show you the QR code again later on. Okay. Not sure what happened, but some students they can scan the QR code. Some students not work. I think the problem is not the QR code, maybe the system. Anyway, let's just start the course first. Okay, so previously we already studied up until the volumes. Okay, and when we have this kind of problem here, we can approach the diff method within with a hole inside. Okay, we call also this part as a washer. We call also this a washer. But basically, it's similar with the disk method. What you need to do is you need to uh, subtract. Okay? Subtract the outer radius, the area with outer radius, minus the area with the inner radius. Okay, and you get this piece. Okay, what we call is usually a washer method. Okay, so you have this method, washer, and the third one that we are going to learn today is it's called cylindrical shell. Okay, okay. Now let's move to what does it mean. Okay, let's start with the graph. This graph. If you have this curve, okay, y equal to x squared minus x cubed, and you also uh, you want to compute the integral under this curve from 0 to 2, and let's just take this y equals 0 as the boundary. So boundary is this curve and y equals 0, so boundary. And then rotate it about this y-axis. Okay? So rotate it here. Okay. Okay. Now, if we want to take the disk and eventually maybe getting a washer, it has this slightly curve, right? So we may feel it's not really a disk with a smooth surface if we cut through here, right? So this left part and the right part, or the top and the bottom, will be um, very difficult to determine, right? Usually, if this is between two curves, we can determine, right? If two curves, the first curve minus the second curve. But this is from one curve, right? So we need to decide which one is our right and our left, right? Okay. Now, if we take this approach with this rectangle, this is not a good approach, not a good approach for this kind of case. Okay? We need to change our perspective here. Okay? So what we are going to do is probably if we take the rectangle here, okay, we take the rectangle here, and let's say we are going to rotate it through here. Okay? Now, if we rotate at this part only, we will get like a cylinder, right? Like a cylinder. Okay. Now, if we try to draw that cylinder, okay, let's just draw the cylinder first. Okay. Let's say we have this cylinder. Okay. Let's say we have the cylinder with the height. Okay, we have the height h, and of course we have the thickness. Okay. Let's say we have the thickness as a delta r. Okay. And we have two different radius. The outer radius, this r2, and the inner radius here, r1. Okay. And the inside is a hollow. Okay. So it's like a can, like when you open your Coca-Cola. Okay. And let's take this R here is the average between R1 and R2. Okay. Let's assume that. Now, if you want to take the volume of this shape, okay, let's compute the volume. So the total volume will be the volume 2 minus volume 1, okay, which means volume 2 is the cylinder with the radius 2 minus the volume 1 is the cylinder inside. Okay, if we minus, we get only the outside, right? Only the outside, right? Okay, let's write the volume. So volume of cylinder is, let me write here. Volume of cylinder is pi r squared, this area, multiply with the height, right? Okay. Now let's write here. Volume 2 is pi r2 squared, okay, and then multiply by h minus pi r1 squared multiplied also by h. We can factorize pi and also h, and we get that. So this is our volume. Now, these two radius here, okay, what we would like to do now, we want to simplify these terms, okay? First is imagine this become a squared minus b squared, okay? Which is, we can have a plus b and a minus b like that, okay? And let's do the same thing with this radius. So we can write down our volume pi h and then r2 plus r1 and r2 minus r1. Okay. Now, so far so good. And then we're going to look here, okay, at this delta r and r. Okay. And let's make some assumptions. Okay, let's assume that the delta r is the difference between these two. Okay. And the r is the average value. So r2 plus r1 divided by 2. So this is the average value or average radius. And this is the thickness. Okay, let's input this delta r and r into our equation here. Okay, and volume will be, let me write h at the end. So r2 plus r1 is we can write this as become 2r. Okay, and r2 minus r1 is delta r, and let's write h. Or simply, we can also write this as 2 pi r, and then let's write h and delta r. We can also break down this volume becomes, this part here becomes the circumference, right? This part is the height, and this part is the thickness. Okay. Or you can also say that these two, or 2 pi rh is what we call here the surface, right? The surface. So if we cut the cut this to, like here, if we have, if okay, for example, in our case here, well, let me just explain this first, and let's go back to the first page. So if we take just example here, okay, if we take this x becomes the radius, okay, the average radius, okay, and we have a delta x or dx here, the thickness, and we have the height. In our case here, the height is our function of x. Okay, we can cut this, and then we are having this is the circumference, okay, of the circle, right? 2 pi and the radius, right? The x radius. The height is a function of x, and this is the delta x or dx in our integral. Okay, or we can also write the area of the rectangle is 2 pi x and f of x, or we call it surface area, right? The surface area of the cylinder. Okay, and we can just put the delta x as a thickness to make it a volume. We can also um, visualize the shell becomes a rectangle, okay, or the yeah, rectangle volume. Okay, so yeah, let's go back here. So this approach here become our approach for any integral that when you take the integrations, for example, this one here, when you imagine and you rotate to something like this, and you rotate here, okay, you rotate to the y-axis, okay? If you try this method and it seems weird, and you feel that, okay, what is this x on xr, which is what is the, like, for example, if you have also similar case, like for example here, and you need to rotate here, and it's a single curve, but you need to rotate here. It's the same case as our idea here. Okay, so we need to use another approach, which is the cylindrical shell. Okay, so we call this a cylindrical shell. Okay, uh, we haven't put it into our limit form, but later I will put it. Okay. So sometimes, in in some cases, um, you can try the disk method or try the shell method. Okay. There is a case that all the methods can be used. There is a case that you can choose which one you are familiar. Okay. Sometimes this can make it easier. Sometimes not too easy, not so easy. So it depends on you to choose. Okay. But for the case like the first one here, and of course this case you should use the shell. Use the cylindrical shell. Okay. So cylindrical shell is more applicable to most of the cases. Okay. But it's not a guarantee that it will be easy. Sometimes maybe the calculation more difficult sometimes. Okay. Okay, let me go through the next section. Let me check. Okay, let me go through. Okay. So similarly, with previous volume method, we are going to have an approximations. Okay, approximations. So we slice also the parts. So we will have several n's, and then we increase the number of the n, and eventually it will lead to our definition of integral. So first is we have the volume is approximately, we can approach to a sum of 2 pi, and let's say this become an xi for some sample. This is average x, and then f at that x, and then a delta x. And when it's going to have a large n, or n getting larger, we can use the limit. And then we can get our integrations, okay? Okay, what's important here is this radius here and height, and this the x is depends on the situation. Okay? It can be y, it can be x. Okay, depends on the graphs. Okay, what's important is you need to first identify the radius. Okay, so identify radius, and the second uh, identify the function for the height. Okay. Now, if we take the first example, like the example from this one here, okay. If we let this become our rectangle here, and let's rotate through here, and this will be what this looks like. Okay, so this is our cylinder, right? So we have the height here. This is the height, or our f of x, and our delta r becomes dx in our case, and our radius here is just x. Okay, so we put all into our volume formula. Start from 0 to 2. Okay, write down the 2 pi, and then the radius is x, and then the height is f of x, or we can just simply multiply with this and the x. Okay, now we can calculate this. Okay, we can calculate. Let's move on this 2 pi outside, and this will be 2x cubed minus x with power of 4. And let's integrate 2 pi, and then 2x4 is x4 over 2, and x4 will become 5. So x5, 5. Okay, and this is 16 over 10, 5, 8 over 5, 8 to 16. Okay. Okay. Let's go to another example. Okay. So find volume obtained by rotating about x-axis region under the curve from 0 to 1. Okay. It is a simple curve, right? That's it. That's our y equals square of x. And let's say this is our 0 and 1. Okay. And of course, this is, you can use the this method, right? You can use the this method. You can have this as your square of x, right? And this is your dx. And eventually, you will get the volume is pi from 0 to 1. R squared is square root of x squared dx, right? And I believe this will be very simple to solve, right? If you use this method. Now, if we try to use the shell method, okay? Okay, we are going to rotate here. So this is what it looks like. Okay. Now we are going to have dy. So we are going to exchange all in terms of y. Now we have x is y squared. Now we have the radius is going to have from here, the shell radius is y, right? And the height, this is the height. But we also have here also the y squared, and this is until 1, so this will be 1 minus y squared, right? So if you use the shell method, then this will be your radius. This will be your height, the green one here, which is the 1 minus y squared. Okay. Then you are using dy. Okay, so it's already y dy 1 minus y squared. We can use the shell also. But I think if you use shell method, the calculation will be a little bit more compared to this method, right? Okay. So if we check it through the shell method, so shell method, to find y, the radius, and then the height is 1 minus y squared, and then dy. A little bit calculation, but I think it's also not really that complicated. So we still can try to, this will be y minus y cubed. And maybe we can have this is y squared. So half minus 1 over 4, half, so half 1 over 4 to pi over 2. Compare with the this method, so this is the this method. Compare with the this method is much more simple. Like for example, this one becomes pi x squared over 2 from 0 to 1, so it's pi over 2. Okay. So why I'm showing you this, because sometimes when you have direct calculation using the this method, sometimes it's much more simple. So you just can stick with the this method. Okay. But there are also cases then when the shell method becomes more simple in calculation. So today my plan is finishing the cylindrical shell and move on to the last part on chapter 6, the average value of a function, the mean value theorem for integral, and chapter 6 will be finished, and go to chapter 7, just an intro and some explanations about the integration by parts and how to apply the method. Okay. So because today is already near the end of the year, right? So we still have at least chapter 7 to discuss, okay? And I believe I will add some additional videos for you, okay, for some section in those chapters, in case we don't have time in class, okay? So we will have a final exam later on January, okay? Maybe on 10, 11, 12, okay? In between those days, okay? We will have a little bit late exam, okay? So when I think the university will be the last day for the final is around 10 or 11. But I think our final exam will be after that, maybe 12 or 13, in between those two. It's still on the same week, so I think it's okay to give the other day as well. And since maybe you already plan to go some vacations or traveling, right? So I believe before the weekends, I hope we already finish the final exam. Okay. So yeah, so January around 12 to 14 or 13, so we will have our final exam. And probably the chapters is until chapter 7, okay? Because chapter 7, I think it's quite a lot, okay? The integration. And also, we have the first quiz, the second quiz. This is the third, right? The third quiz. I also plan to have the fourth quiz, okay? Fourth quiz, which includes the chapter 6, only chapter 6. So not sure when. The only weeks we have is next week or the first week in January. Okay. But I think the first week in January is probably the most possible because you already have maybe your other course also already not really tight, and we can have I think some schedule for our quiz. Okay. Okay. Let's continue a little while. Okay. Some examples. Okay. Another examples. Okay. Find the volume of solid obtained by rotating region bounded by y equal x minus x squared, y equals 0, about the line x equal 2. Okay. Now, to be familiarized, okay, I hope you're already familiar with the questions in typical volumes questions. Okay. So usually they will give you the boundary, which is the curve, okay, or the line. And if you see any words that is start with rotated about or about, right? About line, about y axis, about x axis, which means those regions is rotated about those lines or those axes. Okay. And as usual, I suggest to draw just a sketch or a roughly sketch is okay. Imagine how the graphs looks. And I believe this is how it looks like. 0 and 1 is the root of x minus x squared, x minus x squared. I need to take this a little bit long, maybe around here, because I will have x equal to maybe here. This is x equal to. And we need to rotate this curve or rotate the region about this x equal to. So if you rotate, you will see that it's the same situations with the cylindrical shell when it's first applied. It has like something like this, and you rotate. And if you use this method, it won't work. So you can just look at the shell method. Use the shell method. And this will be the radius, okay? This will be the radius. If you imagine, this is how it looks like when we rotate. So it has like a ring, right? Okay. Okay. Now we need to identify what is our radius now. I think our height is our functions, right? Or f of x in our case here. Our radius now became, this is x, right? Up until here. This is our x, right? So our radius in this part here, because this is x equal 2, this will be 2 minus x, okay? So we can write that as our radius. So this is 2 minus x. So the volume, let me write here, the volume will be from 0 to 1 for that region, 0, 1, 2 pi, 2 minus x. And then the height is x minus x squared, and then the x. And we solve this. We can solve this. Okay. So we will have, sorry, x cubed minus 3x squared plus 2x dx. And I believe you can solve this on your own, and I think it's not too difficult to do so. Okay. But what I want to show you here is when you have any line aside y or x axis, you need also to focus on finding the radius. Okay? Like this one here, okay? Usually you have just x or y. Now you need to relate the radius with your line. Okay. So again, here the x, the variable x, or the radius, or the part of the radius will be this x, right? So you need to use the radius here, which is the 2 minus x. Okay. I hope you guys get what I mean here. So really important to justify the result and finding the through the radius. Okay. Okay. Before we move, any questions on the shell method? Okay. Okay. So basically, the chapter 6 is area between curves. Okay. That's the first one. Volume, the disk method, cylindrical shell. In your textbook, there are there's one section called the work 6.4. We skip that. Skip. And we just move on to 6.5. Okay. So 6.4 skip. Okay. So if you need to maybe focus on your study, you can skip that for a while. So 6.4. Let's skip this. Okay. So we can move to our 6.5, which is the average value. And it's a short sections, and I hope you can understand what the average value means. Now, to begin, okay, uh, we need to understand first what is the average value. Average value. If you're familiar with, like you said, Excel, software, okay, like Microsoft Excel. If you write down some data, okay, you write down A, B, C, D, and it has value 100, 200, 100, 100. Okay. If you write down here average, okay, equation using equal, and then the function is average, and then this is start from what is it? This is 1, 2, 3, or maybe 1, 2, 3, 4, 5, and maybe this is A, B, from let's say B2 to B5. Okay. What does it do is it will take the average value from this, right? Okay. 100, 200, 100, 100, or this will compute in your computer or on your software. That is 100 plus 200 plus 100 plus 100 divided by the frequency on how many data is this? This is 4. And you can get some value, okay? So when you have y average and y is your function, okay, so you can write down y1 plus y2 plus until some number n, and it needs to be divided by the frequency of the number n, right? Okay. Now, because y is a function of x, we can also write this y becomes a function of x1. Okay. Let's make it a sample point so that it can be used for anywhere. And then x2 until some n value. And divide also by n. Okay. Remember, when you have the first time you have the integrations, this is A, this is B, and we decide to take this delta x, right? This rectangle here. And we know that the delta x here is B minus A divided by how many rectangles we have, right? Okay. Now, we can use this n and exchange for the delta x. So this n, let's exchange for this one, okay? So let's change to B minus A over delta x, okay? We can write the B minus A here, okay? And let's write here F. And just keep it simple. And then multiply by the delta x, okay? So this is y average. And then similarly, with the previous integral definitions, we start to write with the sum, okay, of our functions xi and then the delta x. And we know that this part here become our integral. So this average value of a function is 1 over b minus a, and then this will be integration from a to b on fx dx. So this is our definitions of the average value. Okay. It's not really complex. What you need to do is you just have this b minus a, okay, in front of the integral. Okay? Hmm? Hmm? Oh, it means the sample point. The sample point. It means that the sample points means that you can take the the first point anywhere from the rectangle, but the delta is still the same. So it still works the same. So you change to the midpoint, you change to other point, as long as the delta is still the same, it's works. This is just to show you the sample point, just to show you that it will works in either way as long as the delta is the same on all rectangles. Okay, now from the average value here, okay, we can also write the theorem. It's called the mean value theorem, the same mean value theorem, but it's in the integral. And what does it say? This theorem says that if function f is continuous on an interval a, b, okay, then exists, okay, a number c, okay, in this interval ab, where the fc is equal to f average equal to 1 over b minus a, our average value. And we can also write down the integral of from a to b of fx dx is equal this fc multiplied with b minus a. So because we already know that we can calculate the average value, and from those value we know that there will be an x or a constant, okay? That when we put in our constant, we will get the average value. Okay? That's just saying just that. So this is the end of chapter 6. Okay, so chapter 6 end. Okay. Okay, I will maybe upload um, some workout exercise practice on the Google Classroom. You can check later. Okay, now chapter 6 and we move to chapter 7. Okay. Chapter 7 starts with the integration by parts. I believe most of you are familiar with this method. But let me just take a review and how to apply the method. And also the last session, I will show you a simple way to use this method. Okay, and it will help you in a lot of ways. Okay, let's start with the integration by parts. And what by parts means, okay? Why we need to have like by parts? So we need to have some breakdown our formula, okay? Especially, okay, consider you have some f, f, g like that, okay? And you take the derivative. You take derivative, okay? So you have the f dx. This is become f prime g plus g prime f, right? Okay. Okay, let's write f in terms of fg. Okay, so this is f. Let me write here d dx. Okay, and this is also d dx f, and also have g plus g f. Let's say this is d dx. This is also g. Okay, this means that d dx fg or this f, okay, is equal with d dx f multiplied by g and d dx g multiplied by f. Okay, this is the f prime and g prime. Okay, now the next thing, let's integrate this. Okay, let's take integral. So this part here, take integral, integrate this. This parts, we can remove this part because of the fundamental theorem of calculus. Okay, so this will be f g. Okay, and this will give you integrations of g. Okay, and let's just write d dx f as df, okay, to simplify, okay, g df. And this plus f and dg, right? That's right. Exchange the sides, okay? So f dg equal fg minus g df, okay? And let's make some terms, okay? Let's take u is function of x. Let's take v as functions g. So we will have du is f prime x dx, and d phi is g prime x dx. So we will have f of x, dg is g prime x dx. This equal f of x, g of x minus, this is g of x, f prime x dx. Okay, or we have u d phi equal u phi minus phi du. And this is what we call the integration by parts. Okay. Okay. What does it mean and how it works is basically this integral u d phi is our calculation place. Okay. So first, what we need to do is we need to define from our function in integral which one is u and which one is d phi. sometimes we need to try several times to make it some corrections. Okay, and then if we get u and d phi, what we need to find is we need to find du, okay, and we need to find the phi, okay, and then we put all into this equation here and try to solve and find the solutions. For example, again, let me just start with a simple one. Let's look here. Okay, we have ln x dx. Okay. If you're simply looking at this, unless you try several functions in a head to take out some derivatives and put back here, eventually you will get the answer. But if you're using this integration by parts, it will be very, very fast. Okay. So for example, because ln x is easier to visualize this to derive, right? Ln x derive 1 over x, right? Okay. And dx, we can think, okay, just integral, and it becomes just x, right? Okay. So if we assume, and we'll put u as ln x, and we can differentiate, become 1 over x, right? We get d phi is dx, so phi is x, okay? So we can write here, u phi is x ln x, and minus integral phi du. Phi is x, and du is 1 over x dx. Okay, oh, forgot this dx. And we can simply get this in terms of x ln x minus x plus c. And you can check. If you differentiate, this will be a product rule. This will be minus 1, and there will be 1 here, and it will be 0, and it will be ln x. Okay? Okay? I hope this not too difficult to understand. Okay? If you miss out on how to, or miss out the concept behind this integration by parts, oh, it will be very difficult from now. Okay. Okay, let me give you more examples. Okay, more examples, and then from the very easy, and then the most not difficult, maybe most seems complicated, but still we can do it. Okay, let's say we have x sine x dx. Okay. Okay. Now the idea behind this integration by parts is how to choose which one is u and which one is dv, and we can have some suggestions actually. Look at this. This is if we take break down this. Okay, this will be x and sine x. Okay, at least. Okay, we can ignore the x. Okay, because it can be x dx or sine x dx, right? So if we look at this x and sine x, okay, x we can derive easily, become 1, right? Sine x we can derive, become cos, right? If we integrate x, we can also integrate, become x squared by over 2. Sine x we can also integrate, become negative cos x, right? But if you think for x and sine x, if you derive many times, x eventually gets 0, right? Sine x, no, it will recycle. So it will be better to have x as the one that needs to be derived. Sin x integral. Okay. Okay. You can check this logic when you have more questions and examples, and you will conclude that okay, better to have x as the derivative part. Right? So for example here, if we check this u is x, du become x, right? And sine x is this, let me put here, is dv, and v will be a negative cosine. Now, if you look here, we can design the formula, and we can design this becomes, this is negative v du, v is negative, so it's become plus here, and we can have cos x dx, right? This will be plus. Okay. Now, why I'm telling you that we need to have this to be derivable? Because it will be simplified the formula. If you choose this to take the integral, the formulation will have some squared, right? Some squared, and this integration will be more complicated, and it's not solvable. I will let you know later, maybe near the end of our course, how to make this um, method becomes more applicable and easy to use. Okay, this seems very straightforward and still not really easy. Okay, sometimes you will get this integral, you will have another integration by parts that you need to do here sometimes. Okay, like for example, if you have more like x squared sine 3x. So let's say this is the integral. Okay, let me give you some time to solve this one. The x squared sine 3x dx. Okay, anyone solve of it? Okay, another by part. Yeah. Okay. Let's check this. Okay. Okay, so let's use this is u and this is dv. Okay. So let's try this. And we need to integral this become negative cos 3x over 3, right? Okay. Let's write the uv will be minus x squared cos 3x divided by 3. And then v du, this is minus become plus, integral 1 over 3 cos 3x and 2x. Okay, sorry. So it will be, well, let me write 1 over 3 outside. Or 2 over 3 outside, I think better. Okay. And take another integration by parts. Okay. Let me change the color. This is become u is x. And the dv is cos 3x. And v is sine 3x over 3. Okay. Now this will be plus 2 over 3. uv is x sine 3x over 3 minus v du integrations sine 3x over 3 dx. Okay. So we can also finish this part, sine 3x over 3. This will be sine become negative, so plus, right? Plus cos 3x divided by 9. Okay. So we need to multiply and then adding all the value, we will get, this is the first terms, and then plus 2 over 9 x sine 3x, and then it will be plus 2 over 9, or 2 over 27, sorry. Cos 3x plus c, okay? That is our result, okay? So this is integral x squared sine 3x dx, okay? Okay, it seems if you're not careful on this part here, when you are needed to take some integration by parts again, and also consider there is maybe avoiding mistake, this negative part, right? Simply there is a chance that you might get wrong results. Okay? Let's take the simplification of this method. Okay, so imagine when you do this UDV, okay, you need to take this and make it into uv minus integral v du, okay? Which means you need to take this u, take derivative, right? So u is an element in your equation here that need to be derived, right? You need to be derived. And dv is an element that you need to integrate. Okay? So let's write down the terms, the one that you need to differentiate and integrate, okay? Which in our case here, okay, our case here, this is x squared, and this will be sine 3x. Okay? And then let me write the original formula here. When we are doing this part, okay, the whole integration by part, the previous question, we already did this, right? But then from here, we get another uv minus vdu, right? And the signs will be plus minus, and then plus minus, and then plus minus, if you can imagine that way. Okay? So in an idea that we are going to differentiate this, okay, and take it to x, and it becomes 2, and then it eventually becomes 0. This part we integrate, so this will be integrate, become negative cos 3x over 3. Integrate one more, becomes negative sine 3x over 9. And integrate one more, become multiplied by negative, with become positive cos 3x divided by 27. Okay. Now the signs will become from here. This is a good way to simplify the method. Okay. So this is actually the one that you derive, the one that you integrate, which is our uv here. Okay. So this is, we call it sometimes, in some universities, this is called the DI method. Okay. So plus, and this part here, we cross multiply. Okay. So this will be negative x squared cos 3x divided by 3. And this second one, negative and negative become plus. So plus 2x sine 3x divided by 9. And then later on, the plus 2 over 27 cos 3x, and then plus, don't forget plus c. And then the same answer. Okay. Well, in some cases, if you cannot justify where this comes from, then some professor might tell you, this is shortcut mumbo jumbo, blah, 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 right? But this is actually from here. Okay. So we are simply taking these patterns and take it into a table. Okay. So this is simply u dv, and we get du and v, and we cross multiply this way. So if there is nothing, if for example, if you have not n with 0, then you still can use this method also. The last part becomes the multiplications, this, and this multiplications. So this method is actually, if we are going to write down here, this is the original method, okay? How it comes from, okay? So take u and dv, u becomes du, we differentiate, dv becomes v, we integrate, okay? And how we are going to multiply, plus multiply by u, multiply by v, it's become uv. And the second one, because it's not going to be 0 here, then we need to multiply this, but with integration. For this case, we have the integration minus vdu. And when we have a lot of sequences, then we are having just take it into repetitions. Okay, so you have integration by parts, integration by part, integration by part, and you will have like several terms and several terms. Okay, depends on how the DI will looks like. Okay? This will help you to avoid the repetitions. Okay, to avoid the repetitions. So in a case that maybe it's not becoming zero, you still be able to solve it. Okay, still be able. But again, the idea behind this method is still the same as usual integration by parts. We need to identify U and dV. Okay? If we take wrong identifications, we still have difficulty. But at least for calculation, this will help. Okay? This will help for calculation. Okay? Not sure who is inventing this method, but I get it from some university, I think in Singapore and maybe in the United States, some university. They teach this method. Okay, any questions? Any questions? We will have more, I think, exercise later. So that is the introduction of integration by parts. Okay. Oh, maybe I give you another example, but if we don't have time, you can try it on your own. The calculations is, let me just give you the equation first. Okay. Integral e with power of x sine x dx. Okay. And similar, e with negative x cos x dx. Okay, now, okay, we know that sine and cosine going to have, it can be integral, it can be derived, sine, cos, sine, cos, sine, cos. It will be not stop, right? It will be, you can derive as many as you can, right? E also same, right? E derive E. You integrate also the same. But for negative x, the difference is just in the sign. Sometimes it's plus, sometimes it's negative, right? And how do we solve the integral? Because both of them will always repeat it, right? Okay, that's the important one. Okay, to solve this, if you use this integration by parts, maybe you check u and you get dv, you get uv, you get integral v du, and then you get integration by parts again and again. And if you don't, if you are not careful, you will repeat the integration by parts like really, really long. Okay, really, really long. To stop that, you need to check the original question. Okay. Sometimes along the way here, when we integrate, we will get the same equations, and we can solve them. Okay. You can solve with that original equation. So somehow in the between here, you can move the integral part here, move to here, and you can compute this. Okay, let me check. My time is enough. Okay, I think enough. Okay, maybe you can check here. So if we take u is e with power of x, and if let me just try the regular integration by parts. Okay. So du here becomes dx dx, and v will be negative cos x. So we can write down that this will be negative ex cos x, and then minus is plus. Integral phi du is ex cos x dx. And we try to make another integration by part. And this will be plus ex sine x, and then minus sine x ex dx, or ex sine x dx. Okay. If you're not careful from these integrations, you make another one. But you can stop here. You can move this part to here because it's the same terms, right? So that's how you solve that. And the same way, when you have the DI method, like I said before, the DI, we can also use the same way. So differentiate still ex, right? So let's just stop until several times. So maybe this will be integral is, it's negative cos x, and negative cos x integral, it will be a negative sine x. And stop here, and we can calculate, becomes that. I'm stopping at the ex, and sine x is the same as the original one. So I'm stopping here. So the DI method will resulting, this will be negative ex cos x, and then plus ex sine x, and then minus integral ex sine x dx. And you need to write down the whole formula here. And it will be the same results with the original integration by parts. So you can still use the DI method, okay? And then you can solve this, and becomes this. Don't forget, later you need to plus C, don't forget that. And this will be becomes 1/2. Let's write positive first and then negative, and plus C. Okay. So we can also still using the DI method. Okay? Still can use the DI method. Okay. And integration by part is by far the most commonly used to solve. So most of integrations, you can solve it through the integration by part. I think that's it for today's class. Let me give you the QR code. Okay. Let me give you the QR code. Okay, check this QR code. Wait. Okay, this one. Can you use it? If still cannot use, then there's a problem within the system. It's okay now? Okay. Okay. Yeah. You can scan the QR code, and we'll have some feedback time for some questions, 3 questions at most. So online students, can you check it's working or no? Huh? Who's not working? Okay. I don't know what happened. I think the system. The system. Okay. I think some students is okay. Some students not. I'm not sure what's going on. Okay. Yeah, still not working. Okay. I don't know what happened, but this is from the system, so I'm not sure what is going on. So yeah, maybe the system is having trouble. Right. Okay, anyway, let's just move on to uh, our feedback. Okay. This should be work. This should be work because it's not the NTS server. Okay. So we can start this. Okay. Let's start the feedback. Okay. If you guys join, you can join through the website if you see here,mente.com, and this is code 77694276. Okay. Okay, I think we can start. I hope the time is enough. It's just true, false question. We have three questions. The last two questions will be having some calculation. Okay, good. Okay, okay. Okay, let's get the other questions. Second one. Okay, three, two, one. Let's start. Okay, I hope it's enough time. Okay. Yeah, it's correct. 72. Okay. I cannot spell that name. Okay. Okay, let's last one. Okay. Last one. Last one. Three, two, one. Let's start. Okay. So you need to write in a fraction form the result. No need to write pi. No need to write pi. Oh, I'll give you 5 minutes. Okay, 10 seconds. Okay. Okay. Still. Oh, still. Okay, I need your student ID. Who? Okay, I need your student ID. Okay, later. Okay, so that's our class today. So later I will put the uh, exercise on the Google Classroom.